All right, let's start this new segment, geographers, weathering, solution landscapes, and mass wasting. Kind of interesting because we can see some unusual landforms as we go through this particular process. And some of the terms we'll use: weathering. Weathering is when you have the rock dissolve or break down into smaller components. So you've got a solid rock that breaks down into smaller components. Mass wasting would be when those components move due to gravity down the slope. So this could be a landslide, this could be a mud flow, and then erosion is the removal and transportation of that material. Now, one of the odd things about these terms is that you have to be careful when you're using the final term erosion, because it has kind of a vernacular or generic use of when hillsides are going through all three of these processes and they become smaller or they change their look over the thousands or millions of years, we would say those hillsides have been eroded. This valley has been eroded. Erosion has taken place. So erosion can mean kind of all of this together, or it can be very specific about the transportation material. So you kind of have to keep that in mind when you're seeing it in your textbook and I'm using it in the lecture. The context becomes important when we're referring to erosion. And I don't know if you heard that, my dog was growling in the background, so apparently they're very concerned about the appropriate use of the term erosion. So the weathering processes. When we're looking at weathering processes, the breaking down of the rock, there's two factors that are going to have the most influence: is the presence of water. So the drier it is, the less weathering takes place. The moister it is, the more weathering takes place. And also, how solid is that rock? Is there fractures in that rock that allow the water to get in? Now, the weathering, we can break it down into two general areas. The physical weathering, it's a mechanical process, or chemical weathering, where we have that water interact with some of the components of the rock and dissolve into the water some of the components of the rock. So jointing, those are the fractures in the rock. So after the rock solidifies and when we see geomorphic processes acting on the rock, so stresses, whether it's tension or compression or the shearing stress, that's going to cause the rock not necessarily to fault like we would see, but maybe just enough stress where we see some cracks created in it. Those are when we get the water into the rock. So the more jointing there is in a rock, the more weathering we're going to see take place. And also, because we're dealing with a solid object and sometimes we have relatively consistent stress, we may see a pattern in the jointing. So we may see, as in the center one, some parallel lines here at right angles. It all depends on the rock. So we'll see different types of jointing that takes place that affects the weathering. For example, here in Bryce Canyon in Utah, you'll notice the column-like features that we see within the canyon. That's because this rock, the Wasatch Formation, made primarily of sandstone, a little bit of shale and limestone in there as well, but this rock was stretched ever so slightly, so it created the vertical joints, and those vertical joints give us the vertical columns. There's some horizontal jointing in here, and so that gives us some of these unusual lines that you see going horizontally. And so those vertical joints, those allow the water in deeper, and that's where most of the weathering takes place. We can also see, now we talked about this when we talk about volcanic landscapes, the columnar jointing. When basalt cools, you get the six-sided jointing. Well, where's the weathering going to be focused in? It's going to be focused where those joints are and not in the solid material of the basalt column itself. And so as the weathering takes place and these pieces fall off, we're left behind with these nice vertical columns. Shale, we'll get some patterns in it as far as the jointing. These were not cut by saws. These were fractures within the rock, and so that's where we see most of the weathering taking place. And here, on a little bit larger scale, some of the joints, well, that's where the weathering takes place, and so water is allowed in there, and enough material has been removed, and so that's the path that the stream takes. And so that can affect where the stream channel is by the jointing. And if we've got two joints close together over here that are roughly parallel to each other, we can see this little chute that's created for the water. On a larger scale, this is Arches National Park in Utah. This sandstone formation that's in Arches is a nice cohesive block of sandstone. It doesn't have a lot of little joints in it. What it has are much larger parallel joints in it that are be measured in meters across as opposed to inches or feet across. And so as the water gets in there, it creates these fins of sandstone. And if there's a weakness in the rock, we may see a little bit of an acceleration of weathering down and through here. So maybe in this big old block of sandstone that there was a little bit of shale in here, and the shale weathers a little bit faster, so it undercuts the sandstone. And so we see these odd arches. So this is a long fin of sandstone, but there was a little bit of shale down here, and it kind of accelerated the weathering here. And we'll talk about differential weathering a little bit more later. That accelerated the weathering, so it kind of undercut it. And for scale, I don't know if you can see these little black specks where the mouse is. Those are people. And these are massive. And so I encourage you, if you find yourself in central Utah, Arches National Park is just fascinating. When I was there, I expected things like this. For Pete's sake, it's called Arches National Park, so you expect to see arches, but as soon as you get into the park, you're like, there's an arch, there's another arch. Ooh, that's a cool arch. What about that arch? Yeah, it's just chock full of arches. I guess that's probably why they call it that. Now, the two different types of weathering processes, the physical weathering versus the chemical weathering. Physical is a mechanical process. So an easy example of a physical weathering is if you drop a rock on the ground and it breaks, that is physical weathering. It was a mechanical breakup of the rock. Now, when you get freezing and thaw conditions, that water gets into the joint. And what happens to water when you freeze it? For any of you who accidentally froze a can of soda in the freezer trying to get it to cool quicker and then had to clean it up afterwards, you know what happens to liquids when they freeze. They expand. Well, that has a lot of force with it, and so that force pushes apart the rock, makes the joint a little bit bigger. And so over time, the freeze-thaw cycle will cause the rock to break apart. So in California, do we get, sorry, let me rephrase that. In Orange County, do we get this? Do we get frost wedging? Do we get freezing temperatures overnight? Only in the higher elevations. We don't get it in most of Orange County. So this is not something we see around here. Salt wedging is a similar process, and this can happen where you have wet-dry conditions, which we do have. So water will have salts in it, and so the salt crystals, when they get wet, they expand, and when they dry out, they contract, and so that expansion of the salt crystals can break apart the rock. It tends to break apart just the surface. We don't see massive breakup of rock like you would with frost wedging, but it still breaks down the rock as the salt crystals expand and contract. So here it looks like the ice is just lifting it and pushing it away. In Yosemite National Park, if you're there after a cold night where the temperatures drop below freezing, and then during the day it gets up into the warmer temperatures and that ice melts, it's not uncommon to see small rock falls here and there simply because last night when it froze, that was just enough to get that rock to no longer be in contact with the rest of the rock, and then once the ice melts, there's nothing holding it in place, and then it'll fall from down the slope. So we went from, weathering to mass wasting. So another type of physical weathering is called pressure release jointing, and it creates exfoliation. So exfoliation is kind of a peeling process. So especially with igneous intrusive rocks are formed under pressure, and so when they cooled, they're cooled under pressure, and so since they're underground, when the material above them, what's referred to as the overburden, when the material above them is removed through other weathering processes over time and that igneous intrusive rock is exposed, well, there's nothing compressing it anymore. And so it will relax a little and it will want to stretch. Well, solid rock doesn't like to stretch. So as it relaxes, the outer layers, which have the most pressure released from them because they're no longer under pressure, the interior of the rock still has it, that'll fracture. And it'll fracture along parallel lines to the outer surface. This is a rounding process, so anytime you have a corner, it will tend to round that off if you're trying to peel away the outer layer of it. So it tends to create these rounded surfaces, referred to as exfoliation domes. We see a similar process for rock. It's not referred to as pressure release. It's a heating and cooling process when you have solid rock that's exposed to sunlight, and during the evening it's nice and cold, and so that heating and cooling of the rock will cause it to expand and contract a little, and that will also cause exfoliation. So here in Texas we can see this dome-like structure, and the joints are parallel to the surface, and so we have a joint right along here, and as those rocks break away, they'll just kind of slough off and slide down the hill. Now it also allows, these joints also allow for biological weathering, which we'll talk about in a little bit, and those are the plants that are getting there. So we see the joints that cause the rock to break apart, but we'll also allow biological weathering in the process. Here we can see it in Yosemite. See, I told you we're going to be in Yosemite a lot. So Yosemite is primarily a big block of granite. There's other rocks in there. But here it was formed under pressure. Pressure is released and it starts to exfoliate and it rounds off the surface. And so this dome here, half dome in Yosemite, that rounding, the dome part of it is from exfoliation. The half part is because there's a massive joint, much larger than just simply pressure release jointing. This massive joint and glaciation has created this steep face on this side of half dome, and then we get the nice rounding of it. You can kind of see it looks like an onion here. And here's the top of it. So the pressure release, you can see the joints here haven't really weathered that much, but as you get closer to the surface, these rocks have had the pressure release, and so there's been lots of ice wedging over time that kind of breaks apart these rocks. And those are two former students that are right there, father-daughter, who shared their picture with me because it's a great one from the top of Half Dome. So if you guys have pictures for some of the places I talk about or other places that have unusual features, I'm more than happy, with your permission obviously, to include them in my lectures because I always like to show my students being geographers as well. In the backcountry of the Sierra Nevadas, you can see multiple these pressure release domes, these rounding of surfaces in it. We don't really have any good ones down here in Southern California, mostly because of our rock type isn't the right type. But once you get into the Sierras, there's some wonderful ones up there. I just realized there's a dinosaur in this diagram. All right, so chemical weathering. This is where you get, don't write anything down, people. Just bear with us. This slide looks worse than it is. This is where water reacts with something in the rock and either breaks it down, dissolves it, or creates a new compound. And I realize that I just used the term react. For those of you who've taken chemistry, it's not a chemistry reaction. It's just a casual use of the term water. Water does something with something in the rock. So these different types, hydrolysis, oxidation, carbonation, don't stress too much about the subtle differences between hydrolysis, oxidation, and carbonation. We'll focus on carbonation because it's the thing that reacts with limestone, and it's really cool. So if you have to remember any one of these, try and remember carbonation because it creates what are called our solution landscapes. So something in solution is something that's dissolved in water. So hydrolysis, it's where the water combines, creates a new compound. It kind of softens the surface of the rock, and so it allows for other biological weathering to take place. Oxidation, well, we all know what happens when something oxidizes. It's a metal that combines with with water, and it creates an oxide, and so you get a softer material. And if there's iron in the rock, it'll create that reddish color in the rock. That's from oxidation. Carbonation, this is the cool one, because water, and especially if it's slightly acidic water, it reacts with the calcium carbonate, which is limestone, and that limestone dissolves into the water and literally carries it away. So again, remember carbonation, remember this is our solution landscapes. So again, hydrolysis, I'm pretty much certain that there won't be a test question on hydrolysis, but I still want you to know about it because see this grayish tinge here? This is how subtle hydrolysis can be, is that the surface of this has been kind of worn down a little bit because the feldspar reacts with the water, creates a clay. So next time you find yourself in Yosemite, go to a cliff face, and at the very, very base of it, you're going to find a very fine-grained clay material, and you can go, oh, look, hydrolysis. So here you can see the oxidation, the reddish colors that we can find in the Utah area, Grand Canyon. And also oxidation, this is at Cedar Breaks National Monument in Utah. These additional colors is from other metals that are found in the rock. So primarily the red are the irons, but these pinks and whites are also other forms of oxidation. Now, biological weathering, this is where a plant is somehow or another causing the rocks to break apart. Now, there's the obvious ones. If there's a small joint and a seed gets into that joint for a tree, that tree, as the tree trunk expands, it's going to push apart the rock. These trees tend to not be as healthy as other trees, but if anybody's had a plant growing up through their sidewalk in front of their house, their backyard patio, and you see how that plant pushes apart the cement, you can really see how a slow, long, steady pressure on something can cause that gap to increase over time. And then you get these weird oddities of this. There's no soil here for this rock in Zion National Park. A seed made it into one of these joints, some dust collected from the erosion of this sandstone, and then a little bit of water, the seed germinated, and it's kind of hanging on with the roots following the jointing pattern. That's not unusual either for the roots following the jointing pattern. This one down here, this one looks extra strange as to why the hell wouldn't the tree be growing down here where there's soil. This is a farm where the farmer cleared the field of trees to use for agriculture. But this one smaller tree that managed to survive inside of this joint in this solid rock, he left. So we'd have a nice shady place to rest during the day, and so all the other trees were cleared away. Here, just in this solid block of granite in Yosemite, you've got a joint in here. Trees establish themselves, a joint here with the tree. Now, eventually this piece will fall away because it keeps getting pushed away and pushed away. And then the tree will die. I guess it commits tree-aside from the loss of the rocks holding it in place, but it's its own fault. So at Mount Remarkable National Park, I love Australia, the way they name things. Take my world geography class, and we'll talk more about how Australia names things. I'm sure somebody saw this and went, "Wow, that's remarkable." Here, look at this tree. It found somewhere a place to germinate, and then it's following this joint here. Is just enough room to support the trunk as it grows along here. Now this one's died, and what happened here is the joint that was here that was collecting soil had been getting bigger and bigger from the tree pushing it away, and so now the water drains too quickly, so it doesn't get a chance to nourish the roots of the tree, and so it simply has died off. Much smaller forms of biological weathering would be mosses and lichens. And they'll eat away at the surface, soften it over time. Now, again, we're dealing with geologic time, so this can take thousands of years for it to occur. Maybe an animal comes by and starts noshing on the lichens and the moss, and that'll break apart the surface as well. And if anybody's lived in a cold, wet climate that has mosses that grow on like sidewalks and other things, when you remove that moss, it takes away the top layer of the material as well. Now, differential weathering, which we will talk about more when we talk about arid lands, when we talk about desert landforms, is a kind of a recognition that depending on the rock type, they're going to weather at different rates. For example, sandstone is actually pretty resistant to weathering. You kind of have to have a lot of water in it to help dissolve it and break it apart. Where clay, shale, it will actually work like a sponge and kind of hold on to that water so it'll allow weathering to take place. So when you see things like in Grand Canyon, these vertical faces, those vertical faces are sandstone. So they weather really slow. These slopes are shale. And so they weather quicker, so they break down and get carried away faster. So this retreats away, and this is just the only reason this falls apart is because the layer beneath it has been eroded. So it can be on these large scale differential weathering or on a small scale. So this particular layer of sandstone had some shale as a thin layer on it. And so it weathered away and taking away most of the other sandstone on top of it. But this particular spot had sandstone that actually made it in contact with sandstone. So the under part over here and over here didn't weather, where here there was shale. This surface over here had shale, so it weathered away and took the stuff on top of it with it. And so that subtle little area of no shale here and no shale here meant that this was able to survive while it was being undercut from differential weathering. So it can happen on different scales. Again, we'll talk more about this when we talk about desert landforms. Now, our next section will be that solution part of chemical weathering, when limestone, which is one of our 3 most common types of sedimentary rock, so it is really common when water has chemically weathered limestone. All right, thanks people. See you in the next video.